In this problem we have a mass on a string, actually two strings, and it's rotating around some vertical axis of rotation. My suggestion is to do part C first. In part C, you have the mass hanging on an upper string, and we're trying to find the tension in the upper string when the tension in the lower string goes to 0. So when the tension in the lower string goes to 0, we basically take it out of the problem. The dimensions are given, so we can figure out what theta is. Theta is the inverse cosine of 1 over 1.25. And we know what the radius is. The radius is the distance from our mass to our axis of rotation. And so I've marked it here. And that is going to be equal to the square root of 1.25 squared minus 1 squared. And that's 0.75 meters. Okay, so with all of these problems, you should attempt the problem first, stop the video, attempt the problem. If you need some help, some pointers along the way, start the video again. And I'm going to start off this problem by doing a free body diagram. So what's touching my mass is the string. And that's the only thing. And what can reach in from a distance? Gravity. And I'm going to break up my, now once I've got my free body diagram, I've got to decide how am I going to break up these vectors. What coordinate system am I going to use? And I need to find the components of these vectors in that coordinate system. So we always choose one of our directions of our coordinates to be in the direction of the acceleration. So in this problem, the acceleration is radially inward. And so I want my direction to be, that to be one of my positive directions, and that to be my other positive direction, something perpendicular to that. So, I'll call the x direction in the direction of my acceleration, and the y direction vertical here in this case. And so I'll break up, the weight is already in this coordinate system, tension has to be broken up. So I end up with a tension in the y direction and a tension in the x direction and a weight. And this angle right here is theta. And I say sum of the forces equals ma. So I can break that up. I say sum of the forces in the x is going to be ma centripetal, and sum of the forces in the y are 0 because there's no acceleration in the y direction. And so the y information gives me that the tension in that direction equals the weight. The x information tells me that the tension in that direction is equal to mv squared over r. That's the centripetal acceleration, v squared over r. And my t sub x is t times the sine of theta, and t sub y is t times the cosine of theta. The weight is just mg. And so from the y information, I know everything but the tension. So I can solve for my tension. And I got 49.0 newtons. And then I can take that and put it back into my x information to find the velocity. So I've got v squared is t sine theta times r over m. And when I plug everything in there, I get 5.52, and I take the square root, 2.35 meters per second. In this problem, they wanted a rotational speed, revolutions per minute. So if we had revolutions per minute, we'd have to do some unit conversions. There are 60 seconds in a minute, and there are 2 pi r meters in a revolution, and so that's going to equal our velocity in meters per second, and that gives me 29.9 revolutions per minute. So if you understand this part of the problem, now go back and do parts A and B and see if you can do it with 2 strings. So here's the problem for part A. We've got the same mass, same angle, but now there are 2 strings holding it as it's revolving about this vertical axis. It's given that the tension in the upper string is 80 newtons. We've already found theta and r from the dimensions given in the problem. So I'm going to go ahead and draw a free body diagram for this object. And we've got tension, an upper string touching this object. We've got a lower string touching this object, and we've got the weight of gravity. Again, you choose your coordinate system, so one direction is in the direction of motion, in the direction of the acceleration. I'll call that my x direction, and we choose the other direction to be perpendicular to that. So I'm going to change my vector t sub u into components that are in the x and y direction, and same with t lower. So my t upper is going to have a t upper y and a t upper x, and my lower is going to have a t lower x and a t lower y, and I've got the weight of gravity in here too. One quick thing you want to notice when you're drawing your free body diagram: how does the magnitude of the tension in the upper string compare to the magnitude of the tension in the lower string? Well, in the upper string, it's got to be much bigger, because it's the y component is not only counteracting the y component of the lower string, it's also holding up the weight of the object. So we want to check that at the end, make sure our upper tension is bigger than our lower tension. Okay, so let me just jot down a few things that we know. We know that T upper in the y direction is going to be 80, that's T upper, times the cosine of theta, and so I got 64 newtons. I know that T upper in the x direction is 80 sine theta, and I got 48. And T lower in the y direction is the tension times cosine theta, and T lower in the x direction is T sine theta. Okay, now I'm ready to apply Newton's laws. Sum of the forces equals ma. And so I do that in the x direction. And in the x direction I have centripetal acceleration. and I also do that in the y direction, and I end up with 0 acceleration in the y direction. So I'll do the x direction first. T upper in the x, that's in the positive direction. T lower in the x, that's also in the positive direction. Because I always choose my positive direction as radially inward in the direction of the acceleration. And those are the only two forces, and so those have to equal mv squared over r. In my y direction, I have t upper y minus t lower y minus the weight is equal to 0. And so we can use the y information to solve for the tension in the lower string. I get the tension lower y is equal to the tension upper y minus w, and this one was 64, and the weight was 39.2 newtons, and so I end up with 24.8, and this is of course t lower cosine theta, and so my t lower is 31 newtons. Now we can go back to the x information, plug that in over here, and what do I get? I get t upper is 48, t lower in the x is 18.6, and that has to equal 4 kilograms times v squared over 0.75 meters. I get v is 3.53 meters per second. And I want to convert that into revolutions per minute. And so I say x revolutions per minute. There are 60 seconds per minute. Do a little unit conversion. 2 pi r meters in every revolution. And that has to equal 3.53 meters per second. I get x is 45.0 revolutions per minute. And let's take a look. We said that our lower string has to have a smaller tension than the upper string. Our lower string came out at 31 newtons and our upper string was 80 newtons. So it appears to make sense.